this is 26 through 30, and 26 is if reaction 3 is equal to reaction 1 plus reaction 2, then K3 equals K1 plus K2. And now I'm going to show that that is indeed false. This is the one you were talking about.
No, not quite.
The reason this is false is recall that PK3 is equal to PK1 plus PK2. And there K3 is equal to 10 to the minus PK3 is equal to 10 to the minus PK1 plus PK2. And now we can factor this in the exponent differently. This is equal to 10 to the minus PK1 times 10 to the minus PK2, which is K1 times K2. So that's equals K1 times K2, not added together, which we can show it several different ways, but this way is a really good one. So everybody should be comfortable with this one. And this is a fact we're going to be exploiting a whole lot when we get into, which we're already into, equilibrium. Now 27. Under standard conditions, Q equals 1 always. Is that true? Yes.
Yes.
Because under standard conditions, the concentration of every reactant is 1 molar,
Yeah, everything's warm.
and all partial pressures are 1 atmosphere, and 1 times 1 divided by 1 is 1. And so this is true always. The problem that people had was on the actual test I had the converse of this. I said K is equal to 1, and no, that's not true. It could be true in some weird instance, but it's not true always.
Right.
Definitely not. It would just be in some odd cases. Okay, so this is true. And 28 is if a process is spontaneous, then it happens instantaneously.
It means it can happen, doesn't mean it's going to.
Yeah, all that, and this is where we're getting our semantics straight, because the language we use from thermodynamics, the process is spontaneous means it doesn't violate the second law. It means that delta G is less than 0. That's all it means. For a process to be spontaneous, it means it can happen. It's not going to violate the second law of thermo, which is the Clausius inequality, actually. And so it has nothing to do to say that it's actually going to even happen at all.
Right.
It just says that it's not violating the second law, and so this is false. And 29, when the product 1 reaction is consumed and I put in parentheses a reactant, in another reaction, then the two reactions are
Yes.
thermodynamically coupled.
Yes.
And that is very true. That's how we, in fact, that's how we define the thermodynamically coupled two processes. Now, we're at 30. And it's a very simple question. Thermodynamics gives us causality.
Yeah.
And actually, no, it doesn't.
It doesn't?
No. Because we're talking about basically things that, with the path independence,
Okay.
is, it says nothing about the path. We're going to get into kinetics.
Right.
We'll be discussing the path. So we're going to get causality in a little while, a little down the road after we built our foundation. We're going to start talking about the kinetic processes, which is our discussion of the actual path that reactants go to products. But we have no path dependence. And so
That's right.
therefore this is false, which wraps 25 through 30. And now for